today we're going to start the process of learning about how to name chemical compounds. So, our objectives for today are all about that. By the time we finish this section of notes, you should be able to name monatomic ions, name binary ionic compounds, and binary molecular compounds. We'll be covering what it means to be binary versus monatomic. But I'm guessing you can look at the prefixes and get yourself a hint. Okay? We're also going to talk about how to write a binary ionic compound's formula from its name. So we've talked a little bit about formulas in the past. We're going to come back to them, and you should be able to look at the written word name of an ionic compound and write its formula with the correct subscripts. And we'll go over how to do that. And then also, you will be learning how to name polyatomic ions, specifically the oxyanions, which, again, is a new word for you, but we're going to discuss what they are. Okay? All right. We'll start with a formula refresher for you. Remember that chemical formulas indicate relative numbers of each kind of atom in a molecular compound. So in a molecular compound, because there are individual units, you can actually say this is how many carbon atoms, this is how many hydrogen atoms, this is how many oxygen atoms are in it. So in C8H18, we get the subscript 8 on C, which indicates there are 8 carbon atoms. And we get the subscript of 18 on H, which indicates that there are 18 hydrogen atoms in this. All right. This works for molecular compounds, but if we're going to talk about ionic compounds, the formulas look very similar but are representing different things. So, for a ionic compound, instead of having a formula, we have a formula unit, which indicates the simplest ratio of a compound's cations and anions. Because you'll remember, ionic compounds form lattices, so there's not a single molecule that we can point to and be like, oh, there's 8 of this and 8 of that in it, because it's in this great big lattice. So we're looking at the smallest ratio you would need to form this compound. But those subscripts are still representative of numbers of atoms. So in Al2SO4 the subscript number 2 on the Al indicates that you need 2 aluminum ions. The 4 on the O indicates that you need 4 oxygen atoms in order to make 1 sulfate ion. You'll remember sulfate is a polyatomic ion. And then outside of the parentheses, the subscript 3 indicates that you need 3 sulfate ions in order to balance the charge of the 2 aluminum ions. If you want to find out how many total sulfur and oxygen atoms you would have, you can simply multiply. So since the S has no subscript, that means that there's just one of them. So if you multiply 1 times 3, you will get 3 and find that you have 3 sulfur atoms. And the subscript 4 means there's 4 oxygens. Multiply that by 3 and you will find you get 12 oxygen atoms needed. Now this doesn't mean you're going to find an individual Al2SO4 molecule, but it means that if you have some of this compound, what you'll find is that for every 2 aluminum atoms, there are 3 sulfur atoms and 12 oxygen atoms present in the mixture. Formulas are great, but they are clunky to say out loud. So if I'm trying to communicate with you verbally, it's clunky to say C8H18. So instead, we give them a name. CH818 is octane. and this is aluminum sulfate. So, how do we know what name to give something based on its chemical formula? Well, we'll break it down. We'll start at the very most basic types of molecules, and then we'll move on from there. We're going to learn all the naming rules today, which is kind of fun. I found that after I learned these, I started hearing these words in product commercials and reading them on the backs of food labels, and some things that you've heard all your life, for example, carbon dioxide, will start to make sense. So, monatomic ions are ions that are made up of only one type of element. Okay? So, when we talk about an aluminum ion, that's a monatomic ion. There's just aluminum in it, right? As opposed to polyatomic ions that we talked about, where it's a group of atoms forming an ion that are different from each other. So a monatomic ion is made up of only one type of element. Positive ions are called cations, and groups 1 and 2 tend to form those positive cations. D-block elements also form a positive cations, and they have the opportunity to form even higher charges of positive cations because of their ability to reach into those d orbitals. So while group 1 and 2 atoms can only form +1 and +2 ions respectively, D-block elements can form 1, 2, 3, and even 4+ cations. And then negative ions are, of course, called anions, and they are in groups 15 through 17 is usually where you find these. They can form -1, -2, and -3 anions. There are lots of main group elements that simply don't form ions. So you will find some on there that don't form ions. Instead, they share electrons and form covalent compounds. Okay, now we can start our first discussion on naming. Okay, if you're going to name a monatomic ion, it is different depending on if you are naming a cation or if you are naming an anion. Okay. Monatomic cations are just called by their element's name. So if it's forming a positive ion, meaning it's losing an electron, you will just call that ion by the name of the element. So for example, sodium, which tends to lose an electron and become a +1 ion, would simply be called a sodium ion. Okay. So that one's pretty easy to remember. All you have to do is figure out the name of the element. Monatomic anions are named slightly differently. You still need to know the name of the atom, but you're going to drop the end of the name off and just keep the root of the name. So, for example, fluorine, instead of being fluorine, you will just keep the root fluor. And then you will add IDE to the end of your root name. So instead of calling a monatomic fluorine atom a fluorine ion, you will call it a fluoride ion. Figuring out exactly what part of the element's name is the root of the name can be tricky. So there is a list in your book of common monatomic ions, and it will help you get used to what constitutes the root of the name. So what part you should be dropping, basically. Okay. Let's talk binary compounds now. Binary compounds are composed of two elements. So in this case now, we're not just the same element, we have atoms of different elements in them. Because the charges of ions have to balance in an ionic compound, if you know which two ions or which two elements are in your binary compound, then you should be able to write the entire formula out. Okay? If you know that magnesium and bromine are in your compound, then you know that magnesium forms a 2+ ion and bromine forms a 1-. So you're going to have 2 bromines for every magnesium ion that you have. And as a result, the formula for magnesium bromide would be magnesium and then bromine with a subscript of 2. The charges that ions have are not written in the formula because they are assuming that your knowledge of the periodic table and what other elements are in the formula will help you understand their charges. So the charges are assumed. To determine subscripts for an ionic compound, you can use what's called the crossover method. What you're going to start with is you're going to write the symbols for the ions side by side and write the cation first and then the anion after it. Okay. So for our example, we're going to use aluminum and oxygen. Okay, so we have an aluminum ion of 3+ and an oxide ion, because it's a monatomic ion, oxide ion, by itself, 2-. Okay, we're going to write them side by side next to each other. Then cross over the charges by using the absolute value of each ion's charge as the subscript for the other ion. So notice how the aluminum ion's 3+ charge becomes oxygen's 3 subscript, and the oxide ion's 2- charge becomes aluminum's 2 subscript. So we cross over. Then you're going to check the subscripts and divide them by their greatest common factor to give the smallest possible whole number ratios and then write the formula. So in this case, 2 and 3 are the smallest whole numbers possible, but sometimes you will be able to reduce. Okay. So in this case, aluminum oxide would be Al2O3. Let's try an example here. Can you write the formulas for the binary ionic compounds formed between... Oh, actually, I think I did include this in your notes, and I'm just one step ahead of myself. We'll come back to this and practice it in a minute. First, we're going to talk about naming binary ionic compounds because it's relatively straightforward. To name an ionic compound, list the name of the cation first and the name of the anion second. Remember that your anion is going to be the one that has its name changed. You do not need to include the ratio of ions in your written name because, again, it's implied. Now you get to practice. So you're going to give me the formula and the name for the binary ionic compounds that form from these 2 mixtures of atoms. So go ahead and do them on your own. I'll set a timer for about 5 minutes, and then we'll do them on the board. Okay, so first thing we have to do, step 1, is write the symbols for them next to each other with the cation first. So what is... For number 1, which one of these is going to form a positive ion? Zinc. Okay, so we're going to put zinc down. I forgot to change it into drawing mode. And now I've done it too soon. Okay, so we're going to put zinc down.
How do we know if that one forms a positive one? D block.
Because it's in the D block, so it's going to form a positive ion. Because the ones in the D block tend to have, or not tend to have, they have those 2 valence electrons. And so just like other ones, they're trying to lose some of those electrons. So zinc has 2 valence electrons that are in the s orbital. It does have some d orbital electrons available to it, but it's not going to access those unless it needs them. So most commonly, zinc is going to form a 2+ ion. So we'll write 2+. Okay. And then iodine is going to form what type of ion? Negative. And what charge? Yes. So we'll just write a negative sign here. You can write the 1 if it helps you out. Because it has 2 valence electrons in the s block, or in the s orbital. So this all goes back to our understanding of orbitals and how many valence electrons things have. So if you're in the s block in group 1, you have 1 valence electron. If you're in group 2, you have 2, and then the entire d block has those same 2 valence electrons, because the d block is filling a lower d orbital, so they're not filling their outer shell, so their number of valence electrons stays the same. And then when you get into group 13, then they have 3 and 4 and 5 and 6 and 7, and then group 18 has 8 valence electrons. Now it's possible for some elements in the d block to dip into those d block electrons and give some of them up and gain a higher positive charge, but most commonly they're going to form those 2+ ions. If they're called upon to form the 3+ ions, they will, but most commonly you're going to get the 2+ ones. Okay. All right. So now we're going to cross over. So you'll be left, you'll put a 1 down here and a 2 over here. And so what you should wind up with is the Ni2, because the N won't have a subscript because it only has 1. So that should be our formula. And then we have to ask ourselves, is this the lowest whole number ratio? Yes, we can't get lower than this, right? There's no common denominator here that we can divide by.
So you're just flipping the numbers,
Mm-hmm. Yep. And then what would we call this compound? We would call it zinc iodide. So zinc iodide.
So zinc doesn't have to lose anything?
No,
Nope,
it's the
because it's the cation. So the cation just gets to be a cool cat, doesn't have to change his name.
It's negative at least.
You can check yourself too to see if you're correct by saying, so if I have 1 zinc atom or 1 zinc ion, then I have a +2 charge. And if I have 2 iodide ions, then I have 2 individual negative charges. So +2, -2 balances, it checks out. So you know that's right, and then you can reduce from there.
Sulfur's gonna have to be negative. Would it be like a -6? Because
No.
zinc's
Right. So sulfur's gaining electrons. How many does it need to fill its octet?
2.
So it's going to be -2. All right. So again, we're going to start by writing them side by side. Zinc is still our cation with our +2. Okay. And sulfur now is our anion. What's sulfur's charge? -2. Okay. So we can cross over 2, and 2. And if you check, right, 2 times positive 2 is a plus 4, and 2 times negative 2 is a minus 4. So we know that this is balanced, because the charges have to balance each other. Is this the lowest common whole number ratio that they can have? No. The what did they call it? The greatest common factor for this is 2. So you divide by 2, and you should wind up with just ZnS. And what would we call this compound? Zinc sulfide. Indeed. Good job. You did it. On page 215, not only do they list common monatomic ion names, but they also list their charges. So if you are struggling to use the periodic table to remember what their charges should be, page 215 in your textbook is a great resource. Okay. I'm going to exit this mode. Stock system nomenclature. You're going to hear the word nomenclature a lot in this chapter because nomenclature is like the process of naming things. So when they say nomenclature, they're talking about a naming system of some kind. Some elements, like iron, form 2 or more cations that have different charges. So we talked about that. We said there are some that can form multiple with different charges. Okay? There are no anions that form more than one charge. So if it's an anion, it's always going to have the same charge. Only cations form with multiple charges. So just a tidbit of knowledge for you. The stock system of nomenclature is used to tell apart ions of these elements. Okay? This system uses a Roman numeral to indicate an ion's charge. So the formula won't indicate charges, but in the name of it, you can. So there is a parenthesis placed immediately after the metal's name. For example, iron, parentheses 2 in Roman numerals, or iron, parentheses 3. So that tells you if it says iron, parentheses 2, then that means that this is an iron cation that is forming a 2+. If it has 3, then it's forming a 3+. And so you could have this for 1 or for 2 or 3 or 4. So you could get all the way up to IV in parentheses there. In the name of the binary ionic compound, the Roman numerals are included after the name of the cation between it and the name of the anion. So, for example, copper 2 chloride. They don't need to include the Roman numerals in the formula version because you will be able to see in the formula how many of the other atom is present, and if you know its charge, then you'll be able to predict the charge of your atom. So they don't need to include the charge in the formula. But in the name, there's no way of indicating that, so they have to include it. All right, let's try a practice problem. Write for me the formula and the name for the compound formed by ions of copper and sulfur. And their charges are listed up there, so you know which ones we're doing. That was the bell, so this will be our bell ringer at the start of next class period. I'll go over this on the board.